All right, so the example 4 that I brought in was not only to remind you about how all the transformations we have learned from our past, learning we apply into the graph, we apply to the graph of an exponential function, but also to introduce a further generalizations about some main characteristics of the graph of an exponential function. So again, just to remind you about the transformations applied to a graph is not the only intention of example 4, but I want to use example 4 as later on as a way to introduce you and explain some further generalization about some main characteristics on the graph of any exponential function. Okay, and so let's now get into that. So after looking at the transformation primarily as a steps, okay, let's get into that. So on my other board, all right, so now you can see that throughout example 4, part A, I focused on this function f of x. I may not name it correctly anymore, but it's the same function here. F of x equals 2 times 3 to the x minus 1. So that was the function. Okay, and then the one in part B, we looked at f of x. And again, I may name it slightly differently, but it's the same function here. Minus 3 times 1/2 to the x plus 1. Okay, so these two functions, right after example 4, mainly what should have caught your attention, whoever viewing the lesson here, what should have caught your attention is that these are generally in the form of an exponential function. I just now realized I didn't put enough space for myself. So any of these two is in the form of an a to the x, an ordinary exponential function, regardless of a base greater than 1 or a base less than 1. But these two functions, these two exponential functions from our example 4, primarily any one of these is in the form of a constant coefficient. Like say we had a 2 multiplied with a 3 to the x. We had a minus 3 multiplied with the 1/2 to the x. So a constant coefficient multiplied with the ordinary exponential function and plus with a constant k. We want to explore and discover even further details and eventually come up with some some solid generalizations about this further general form of an exponential function. Okay, so this is what we're heading into right there. So any of these that I introduced earlier in example 4 is primarily in this general form. But before I get a little further, you start wondering, so wait a minute, but I thought, and you may already have this thought with me as well, that at the end of that introduction lecture where I introduced about any exponential function, I mentioned that more generally, according to the extended definition of an exponential function, then any function in the form of a c coefficients times a to the mx plus b plus k. Any of one of these this is even a more general form. But why am I only focusing on this? Because right now, this exponential component right here, this exponential part of our general form here is only just one single, coefficient 1 for the x and then plus a 0. Whereas here it's intended that we have an mx plus b. So where's that mx plus b? The truth is, and later on I will give that explanation in detail explanation, but the truth is, even though we have a much bigger family of general exponential functions, but we only need, take my words on this, we only need to focus on this form right here where it's a constant coefficient multiplied with an ordinary or a basic exponential function, a to the x only, no need to have an mx plus b here, okay, and then plus a constant term. We don't really need to have anything like this, okay, and I will get to that detailed explanation of why we can only focus to this form right here, okay, we will get to that later on. All right, but so now let's pay all of our attention, and that's why, again, as far as transformation, you see having an mx plus b in our function also these are responsible for horizontal transformations, but mostly throughout example 4 I only focused on the combinations of all the vertical transformations. Again, because I was planning to target at this general form where mostly just the vertical transformations involved right here, and I completely ignore about all the horizontal transformations, and I will get to that solid explanation why we skipping those. Okay, so now once we're all clear with all that, all clear with the plan that we're skipping those forms where some horizontal transformations involved, then let's focus on that. The overall generalization I would like to point out here, and like I said back to that part I said earlier, I brought up these two example problems here, not only to remind you about the transformations exist out there that can be applied to the graph, but also to push into a further generalization. So what is that generalization I would like to point out? Okay, so now on my other board, just consider any simple or basic exponential function, a to the x, okay? And then we have already learned the following facts in the earlier part of this lecture, just right before example 4 right here. Now, if a is a positive, if a is a value, a is always positive, but if a is a value greater than 1, then our graph is a rising graph. Okay, rising graph from the left to the right. So the major characteristics I want to focus now is that any exponential function, at least for now we're looking at specifically the ordinary one right here, then in these forms, either greater than 1 for the base, the graph has a y-intercept at 0 and 1. So y-intercept is one important characteristic. So the number one thing is the y-intercept is one fascinating characteristic of any exponential function. Okay, that one is that graph right here for any a to the x where a is greater than 1. The graph we have agreed earlier is going one way, rising from the left to the right, and intercepting with the y-axis or the vertical axis right at that point 0, 1. So it has a y-intercept. But 0, 1 is just for the case where it's an ordinary function, okay, an ordinary exponential function, that simple basic one, just a to the x. And then in case where a is less than 1, and of course positive, then the graph is going this way. Okay, it's a graph that's falling from the left to the right. You have seen this. There's no need to keep mentioning it. Okay, and it agrees again that it has a y-intercept at 0, 1. All right, and this is why, it's such a special characteristic. We want to push it further into we want to look at the transformation. We want to use the transformations to explain how, in general, how a general form like this, even more than just a simple ordinary exponential function, will cause some change to the y-intercept of an exponential function in general. Or in other words, we want to come up with a generalizations of where we can quickly identify the y-intercept on an exponential function in a much more general form like this. Okay, because the first characteristic, the first major or important characteristic or fascinating characteristic, whatever you want to say it, is the property about the y-intercept right here. Okay, so right now it's at 0, 1, but only for the case where your function is an ordinary function, an ordinary or the simple or the basic exponential function, however way you want to call it, just the simple a to the x. Then the y-intercept, yes, it's at 0, 1, 0, 1. Doesn't matter which shape it's going. All right, and now so in y-intercept is one major characteristics that we want to get into and eventually come up with the generalizations regarding that form, constant coefficient time a to the x plus k. The next thing that we have already seen throughout our investigations earlier, again back on an ordinary exponential function, then any one of these has a horizontal asymptote. So it has a horizontal asymptote. Is here. Okay, horizontal asymptote, HA is short for horizontal asymptote at the line y equals 0 or namely the x-axis. Okay, This case is the same, even though the base is positive, of course, but lesson 1, we also have an HA at the y equals 0 line right there, or the x-axis. So where the horizontal asymptote is found is we're going to get even more detail into that, but mainly as another major characteristic, any one of these exponential function has a horizontal asymptote. So we want to explore and come up with a final generalizations about the horizontal asymptote on any general exponential function. Okay, so horizontal, that's the 2 major characteristics that we want to come up with a generalization. And so I purposely want to give the explanation and arrive at the generalization of these 2 major characteristics on any exponential function using the transformations understanding. And that's the reason why. All right, and so now these are what we are about to head into. We want to see how these 2 characteristics will be quickly identified, or will be generalized in a more general form of an exponential function. And like I said earlier, we primarily only focus on the forms where it has only all the vertical transformations. The vertical scaling is here, and the vertical shift is here. All right, so now one by one, let's investigate. So I put the 2 functions where we worked with in example 4 here on the board, but now allow me to erase one because I want to save all this board space here for that first one here. And then once we've had some generalization, then we're gonna use the second one here to confirm our understanding. Okay. All right. So now again, our target is to investigate about the y-intercept and the horizontal axis of a function that in a more general form like this, of an exponential function in a more general form like that. Okay. So now I even need to write this even further up so I can maximize my amount of space right here. All right. So the function that we first looking at, and we saw this already in our example 4, that we saw the real action, but that example 4 was only to show you, hey, we have these transformations, so it caused changes to the graph. But now, of course, after the graph is changed, we want to recognize the horizontal asymptote and the y-intercept specifically on those descendant function. Okay. And yes, this is generally we want to look at f of x equals some c times a to the x plus k. All right. So let's put that kind of side by side like that. All right, so now I'm going to swing by Desmos, my favorite graphing utility. All right, so now on my web browser, allow me to show complete view of the web browser with Desmos right here, where we can see the command entry lines right here, okay, with all the command input entry lines right here. So I'm going to start out with, so just like how we were doing that in example 4 right here, then 3 to the x is our parent function. Okay, so on Desmos here, allow me to call 3 to the x that parent function, because I'm still using, again, as I was saying, I'm staying focused on the transformation and use the transformation steps we've learned as a way to explain the generality about the horizontal asymptotes and the vertical intercept and the y-intercept. So that's why I still need to bring in a lot of those, or intensively the concept about parent function and the descendant function. Okay, so again on the graph. So now the parent function is 3 of x. So we shouldn't be surprised about this. So, and this is the parent function for this function I'm about to bring up like that. All right, so it was 2 times 3 to the x. And indeed, I believe I have a little typo over here. It should have been minus. Actually, now I look back at my example, 4a, and I have corrected that. It should have been 2 times 3 to the x minus 1. All right, so the parent function as we have agreed throughout example 4, that's 3 to the x. And that's why on Desmos, the web browser with Desmos right there, I had a line saying f of x equals 3 to the x. Okay. All right, so this is our parent function. And so namely, as I already discussed this throughout example 4, so the function that is 2 times 3 to the x minus 1, or we can call it g of x, here with decimal, it really means the function that we really are aiming at, that I wrote on the board, really is 2 times the parent's function and minus 1. But now minus 1 allow me to write that in the form of add a negative 1. Okay, so because algebraically add a negative 1 really means a minus 1, but I want to show the fact that I want to write it in the way that this is our constant term, that we're adding a constant term, and the constant term is negative 1. We multiply our function, our parent function, with a coefficient, a constant coefficient, positive 2. All right, and so now let's look at the graph. So I don't need to explain into detailed steps about how the transformations work anymore. But so our parent function has the following graph. And with this parent function, we have a y-intercept at 0, 1, and the horizontal asymptote for this function. So for this function, the horizontal asymptote is at y equals 0. Okay, so before I bring up the graph for this descendant function, let's quickly summarize down the information regarding y-intercept and the horizontal asymptote for this parent function. Okay. So on my board, as far as the parent function, and so to agree with decimals will work right here, how about let's call this g of x, okay? And I sincerely apologize for keep switching, but so f of x here, let's regard to that as our parent function, 3 to the x in this case. And we saw the graph there, okay? No need to swing back to that. And so the graph is, and we can easily sketch this. Just that shape right here, one way rising. Forgive me if I'm off scale, but definitely as far as the two major characteristics, we're looking at a y-intercept right at 0, 1, just like what we saw on the graph. And we have, in this way right here, we have a horizontal asymptote. The other major characteristics, our horizontal asymptote is at HA, okay, is happening at the x-axis, which is that line y equals 0. These are the two major characteristics on the parent function. Okay, so now let's look at this 2 times 3 to the x minus 1 function. And as I wrote on the board, I mean on Desmo's command line, I was seeing this. I see this as plus a negative 1. Plus a negative 1. And at this point, I think it's better that I write that in red ink. Okay, even the coefficient here, because I just want to emphasize on the fact that it's the same parent's function, but we multiply with a constant coefficient and we add with a constant term. All right, so now, now I'm about to show the graph of g of x. All right, and so at this point we only need to focus on the y-intercept. So now allow me to hide away the 3 to the x to keep things less confusing. So for this particular graph right here, the y-intercept is at, now it happens to be the same with the earlier one. It happens to be the same with the parent one, okay? But it's not always the case, so don't take that as a generality. It happens also as 0, 1. And then this particular graph right here in blue has a horizontal asymptote at that line. It seems like y equals negative 1, because the graph this time crossed through the x-axis and sink below that, but then it appears to be asymptotic to a line. And so the horizontal grid here is making it clear that this graph right here is having a horizontal asymptote, but this time it looks like, in what my eyes are telling me, it looks like y equals negative 1 is the line being the horizontal asymptote. Okay, so now let's document our observation here. All right, so for the actual function, the descendant function, g of x, being 2 times 3 to the x plus with a negative 1. The parent's function is the 3 to the x, so g comes out from multiplying the parent's function with a positive 2 first And now I'm saying first and next and last because there's always that order of operations heavily involved in any of these problems. And that's why with any parent function we have the multiplication comes first. Multiplication or division comes before adding or subtracting. So that's why the parent function multiply with the coefficient first and then add with a constant term. But now in the end, the graph came out as following. The graph for this particular function, as we have seen on the the picture of, on the computer screen earlier, we had a line down here being a horizontal line at -1. Okay, so that line here is y equals -1, and our graph was behaving as following. We had a y-intercept at 0, 1. Okay, and the graph was like this. It did go through the x-axis. Okay, but it's asymptotic with that line that it's having a horizontal asymptote at y equals -1. So this is what we document from our observations right here. Okay, so the vertical intercept is here. Y-intercept is at 0, 1. It happens to be the same with the original parent function, but don't take that as an always. Okay, don't take that as an always. But HA for this problem is at y equals -1. Is at y equals -1. So now I was saying earlier I wanted to use the transformation step that I introduced in example 4 to explain how the new graph right here, how the descendant function arrives at this 0, 1 for the y-intercept, and also how this y, the value for the horizontal asymptote, arrives at y equals -1. So recall again, vertical transformations deals with any property of a graph that relates to the y value. Vertical transformations apply on all the y values, anything that relates to the y values of our graph, of our input. And so that's why now, see, y-intercept, right? Now it's at 0 for x, of course, but we want to know why it still stays at 1. We want to know why it still stays at 1. Okay, why it didn't go away to a different point. But once again, we want to find out using the transformations understanding. We want to find out how it went from 1 to still remain at 1. Okay, and then we want to find out how the horizontal asymptote from the parent function that was at y equals 0 now came to y equals -1 there. Okay, and so on this board, I have left this here long enough. And so now allow me to again briefly bring back the table approach. I've always been using that to explain the transformations to my students. Anytime I'm doing transformations, I myself personally, and when I teach, I always use this table approach right here. So now for the original parent function, f of x, okay, we only need to tackle down, we only need to focus right at the y-intercept. So the y-intercept on this function, when it was in example 4, I consider the y-intercept as one of the guiding points. And now instead of building the complete tables of values for all the guiding points, we only need to focus on the y-intercept. So the y-intercept of the original parent function is there. Okay, 0 for x, 1 for y. Okay, 0, 1. And then so the next step right here, again, vertical scaling comes up before vertical shift, simply because multiplications or division must happen before adding or subtracting. Okay, and so now that means in the next step, I'm gonna, the next column, I'm gonna think about how this point, how the y value is going to be adjusted. The y value for the y-intercept here is going to be adjusted after we multiply every y value by 2. And so multiplying every y value by 2 here, our y-intercept, supposedly 0, 2. That's the first step like that. So 2 multiplied with the parent's function really means if it was written down, it looks as following. 2 times okay, this is 2 times our function, parent's function. So as back to what I was saying earlier, if this was written down in formal term, this is 2 times 3 to the x. This is what that function, 2 times as a coefficient, 2 times 3 to the x. Okay, So if it was only that function, then the y-intercept would change to 0, 2. Okay. But then in our case right here, this is not our final step. After multiplying the function output value by 2, we have the next column here by subtracting or just simply adding a -1 to every y value. Add a k to every y value. So now I'm going to add a -1 to every y value. So that's why now for the most recent y value right here of our y-intercepts. So this is all about the y-intercepts, but the most recent, after the most recent transformation, from the most recent step right here, I'm gonna add -1. That is the reason why. So now with this version, I should write that in blue right here. All right, so in blue ink, right, 2 times f of x plus -1. Okay, so now in blue ink, that's why I arrived at 0, 1 again, because 2 plus a -1 ended up with 1. So now let's particularly focus only on the y value. So what happened here? This final 1 right here really came out because this final value 1, it's kind of ridiculous that I'm writing this down, but this 1 right here came out as a sequence of work right here, as a sequence of operations that applied here. So from our original parents, the y value on the intercepts was 1. Okay, was 1, and then we multiply that by 2. Okay, and then we add with, and so I should have written this in red ink right here. This is from the parent function. We multiply with the coefficient 2. All right, and then we add with a -1. And think about it this way. Now we're particularly or specifically talking about the case where it's always multiplied with 1 here, because our original, this is an ordinary exponential function. 3 to the x is an ordinary exponential function. So that y-intercept is always at 0, 1. So that y value is always 1. Always 1. And that's why in this blue version here, it's happened to be because it's 2 times with that always 1 value and then plus k. So it looks like I recognize the following, but I only saying that I recognize the following. The final intercept here, it looks like it's always 0. It looks like it's always 0. Right? This is my observation. It's always 0 for the x value, but then this is 2. That 2 here being the same with that coefficient in front of our function. Okay? 2 plus -1. I purposely write it in that way, like that awkward way right here a little bit. But see, I want to display that, or maybe I should have written that in red ink right here. Okay? 2 was the coefficient in front of the ordinary function, and plus with -1, the value of the k here. Because now I'm slowly bringing viewers or learners into that general form here. So c is that constant coefficient we introduced in front of the ordinary exponential function, and k is that constant term we added after we multiply. Okay, so it seems like, so in what I was saying earlier, I recognize that for now I recognize that it looks like to come to the final y-intercept right here, it's always 0 for x value, but the y value on the y-intercept seems like it's related. It's always seems like it was here the coefficient value, and add with that constant term, whichever value of the constant term is coefficient, add with a constant term. So I came to a suggestion. I came to an expected generalization, but I'm only saying it's a suggestion, it's an expected generalization, but we need to confirm. We definitely need to confirm. So it looks like y-intercept is at 0 for x, but c plus k. Okay, c plus k. But we need to confirm that. We need to confirm that. So let's hold it right there. All right, we need to confirm that. All right, so now, but before I get further, so before I can confirm the y-intercept for this, let's look at the horizontal the asymptote. Okay, let's look at the horizontal asymptote. So back on this board, the original parent function or the ordinary 3 to the x function has the horizontal asymptote at y equals 0, the x-axis. And I made that generalization earlier. Anytime it's the ordinary a to the x function, or anytime it's the ordinary exponential function, the horizontal asymptote is always at y equals 0. At y equals 0. And now for this version right here, where we multiply our ordinary exponential function with a coefficient, and then after that we add it with a constant term right there, we arrived at the y equals -1. Let's again use the transformations understanding to explain why and how we arrived at this, and then from there we're going to recognize into a generality. Okay? So, admittedly, I've never done this throughout all of our discussions on the transformations because it didn't happen at that time. But now on this, we can also do the following. I can also use this table of values, but surprisingly, I only do the singularly y value. Y value of the vertical asymptote. See? Y equals 0 for the beginning parents function. I can also, instead of a pair of values, I only simply focus right on the y value. Okay? I only need to focus right on the y value. So that's the y value of the horizontal asymptote of the original parent function. And so now if it was a 2 times 3 to the x, or generally as a transformation step, if it was 2 times the parent function, again, vertical transformation, the vertical scaling happens before vertical shift. Okay? So in that way, now the y value here, if it was simply 2 times 3 to the x, or just 2 times the ordinary exponential function, then the HA would come out as following. 2 times y, we multiply the constant c to every value, to every y value. So 2 times y equals 0 again. And that's why we ended up with a new y version, y equals 0. See, 2 times y of the original value, it gives me a 0 again. So that's why if it's 2 times 3 to the x, we also end up with a horizontal asymptote being at y equals 0, being at that x-axis again. Maybe before I rush to the next step right here, let me quickly swing over to decimals and explain. Okay? Alright, so with decimals right here, see, if it was only without the constant term right here, the blue graph, this blue graph right here is the graph for 2 times 3 to the x. See, clearly and apparently it's having the horizontal asymptote also at y equals 0. Okay? And so the mathematical explanation is given here. It's simply because we multiply that constant coefficient. See? So once we have, for a vertical scaling, we multiply that constant coefficient in front to every y value. So now we extend that understanding to even include the asymptote. Horizontal asymptotes relates to y value. So every y value must be multiplied by that constant coefficient. And that's what explains for why, that's what explains for the reason why even though we have a new function 2 times 3 to the x, but it still arrives at that same horizontal asymptote y equals 0, because 2 times 0 is still 0. That's why. Okay, but now let's really move on to the next step. So now from here, see, our final destination here is after multiplying 2 to every y value, we're going to add the -1. And so in that way, so now the horizontal asymptote version for this final function. So this final function, yes, it was 2 times 3 to the x plus a -1, as we already saw from the other board right there. Okay, so the HA, the horizontal asymptote for this, can be explained as following. Okay, so from the very previous step, y equals 0. Okay, we're going to multiply by 2 first. We already multiplied by 2, but now we're going to do the following. We're going to, from the y value, we're going to add a -1 to that. Add a -1 to the preceding y value. The preceding y value was here. That was where our horizontal asymptote was located at in the preceding step. So now from that same y value of the horizontal asymptote, I'm going to add a -1. Just like that. We add the constant k value to every y value. That causes the shift. Negative causes a shift down. Positive causes a shift up. That means now we're looking at equals -1. See, because it was 0. Okay, it was 0. So now really it's 0 plus -1, the value from the previous step. And that's the reason why. We're looking at. Y equals -1 being the horizontal asymptote. Okay, being the horizontal asymptote for this. And so now let me even push it into a further detail here. We agree that it's always, for any ordinary, here I'm using a base greater than 1, but for any ordinary exponential function, horizontal asymptote originally is always at y equals 0. And so now, even though we underwent 2 steps of the transformations, but the first step, by multiplying a value, it's always going to come out with 0. And then with that middle steps being 0 value, we're going to add with a constant. That's why here's a kind of like a generalization. I'm at this point over 80% sure over here. The horizontal intercept. The horizontal intercept is always at y equals the k value. The k value, because see, it was 0 always for the original one. We multiply with any c value. But c 0 multiplied with any value equals 0. And then we add with a constant k. So that's no doubt about it. Horizontal asymptotes must be also 0 from the original parents. Multiply with c makes nothing difference. 0 again, but plus k. And that's why here I predict that for any general, the c times a to the x plus k, I predict that it's going to have a horizontal asymptote at y equals k. But so at this point right here, I only use one example right there with the brief explanation right here. So I can only say, that's how math works. I can only say I'm about over 80% confirmed. So let's confirm our observations. So at this point, we have already made some generalizations, but we're just about over 80% confirmed, over 80% sure. The number one, y-intercept, when our function is transformed in the form of a c times a to the x plus k right here. The y-intercept is always at 0 for x, plus the y value being c plus k. Okay? And then for horizontal intercepts, the second important characteristic that I was mentioning, okay? Then it seems like I recognize that the rule here is y equals k. The value, the k value that we as a constant term that we added to the c times a to the x, that value k simply becomes our final the value for the horizontal intercepts, y equals k. So right now it looks like we already recognized some generalizations regarding y-intercept and horizontal asymptote on any general exponential function like this, where it only involves the vertical scaling and the vertical shift like that. Okay, so but then let's confirm that. All right. So now I use that example 4a to explain, and I explain that through all the vertical and the transformations as the explanations behind the scene. So now we're gonna see that explanation again. Okay, so back on this board. Okay, now let me look back at example 4, but our part B. Example 4, but our part B. All right. So the function we used in example 4, part B, now this time I'm going to call that straight into it, g of x. Okay, and it may not be the same with whatever naming I particularly used in example 4, part B, but it's the same function. Minus 3 times 1/2 to the x plus 1. And so again, this function, the way how I see it, it has that parents function 1/1/2 to the x. This is the ordinary exponential function. Yes, admittedly the base here is less than 1. Okay, but what I want to show is it's in the form of a constant c. our constant c, our constant coefficient is -3, multiply with that, and then we add with a 1. So this is our k value, and this is our, and we adding. All right, and so now as far as an underlining, this is c right here, and this is k. So now I'm making it clear that this function g of x is in that general form of an exponential function where we have a combinations of all vertical transformations applied to an ordinary or basic exponential function a to the x. Okay, so now let's get to it. Okay, so now as a reminder, I don't think I need to swing over to the decimals yet, but right here we call the parents function. We can call the parents function f of x. This is what we recognize from our example 4 over here. The parents function f of x, we call it that way, but really it's that 1/2 to the x, 1/2 to the x. Base is less than 1. Positive base, of course, but less than 1. Okay, and so now this is what I see right here. This is what I see. And I don't even, again, as I said, before I even need to get to the web browser with decimals showing in front of me, I can already expect that with a graph like this, with an ordinary function like this, an ordinary exponential function like this, where base is less than 1, my graph is expected to do the following, to display the following nature over here. It will be a falling down graph from the left to the right. That's what we've learned already and already clear about that. We will have a y-intercept right here at 0, 1. And this is the first major characteristic that we've been learning about. Okay, and would like to come to a generalization on the general version right there. All right, and then with this particular function, with this particular parent function, we already understood as a generalization on the ordinary function that it has a horizontal asymptote at y equals 0. Y equals 0 again. So now we even more affirm that, hey, in general, anytime we're looking at an ordinary or a basic or a simple exponential function, it will always definitely, and regardless of whether base is above 1 or less than 1, horizontal asymptote is always at the x-axis, or y equals 0. Or y equals 0. All right, so these are the two major characteristics. So let's now switch over to decimals. Okay, to look at the graph for our version here, for our version of g of x, which is being the function 1/2 to the x, multiply with -3, and then add 1. Let's investigate that. All right. All right, so now this is my graphing utility with decimals right here. This is our parent function, 1/2 to the x. And this is just to show you that the graph of this parent function agrees exactly with the imagination I have with the expectation I wrote on the board earlier. And we have a horizontal asymptote right at the x-axis. Okay, so the x-axis is the horizontal asymptote, and the graph is a falling curve from the left to the right, and it has a y-intercept right at 0, 1. All right, so now from that point, let's now look at the descendants function that's created by f of x, but multiply with a -3. So -3 is a coefficient multiplied to f of x. Okay, and then we're going to add 1. Okay, so after that we can add 1, and you can see that anytime I'm typing in these inputs right here, these are functions, either using decimals or using a calculator, I follow the order of operations as well. So from where our function f of x is the original parent function, I multiply first, and then we add or subtract a constant value, a constant term, like that. Okay, and so and yes, indeed, this is the same as -3 multiplied with the 1/2 to the x, just like how you have seen on the board earlier. This is what it is right here. So g of x is -3 times 1/2 to the x plus 1. But now if we're typing the input like this, decimals will not recognize. So that's why I need to erase this part right here and only leave that as generally a -3 as a coefficient, multiply with the function f of x, the parent function, and then plus 1. All right, so now let's bring up the graph. The graph here is in blue. The graph for g of x is in blue. All right, so this time let's find out about, again, y-intercept and horizontal asymptote. Things completely change. Okay, so with our understanding about the transformation, and I already explained this as well back in example 4, and now no one is surprised why we have the graph appears to be a flipped version compared to the original parent function. Okay, and that's all due to the negative sign. But then that's not important in this particular discussion here. What I want to find out, what I want anyone viewing this lesson to focus to is the two major characteristics again. Okay, y-intercept and a horizontal asymptote. So it looks like right here from the picture we're seeing right here. And let me swing back to the board and record down what we have observed here, what we have seen from the graphing utility. So according to the picture that we have seen, okay, with decimals, this function has a graph. All right, and it looks like we had a y-intercept somewhere down here below the x-axis, okay, and we had a horizontal asymptote somewhere up here above the x-axis, okay, and it goes as following. All right, the graph goes like that, okay. That's what it looks like. All right, so now let's even investigate even further. So we need to go swing back to decimals and use our own estimates through the eyes like that to find out where the graph physically crosses through the y-axis and where it's asymptotic with the horizontal line right here, or where that horizontal asymptote is at, based on our own estimation through the eyes like that. Okay. All right, so now with the graph, with the actual graph showing here, the horizontal asymptote appears to be at y equals 1. Okay, so now I think it's better that I'm hiding it, that I would hide away that the original parent function, so that the horizontal asymptote, the grid would come out more easily for us to recognize right here. But it happens right here. The horizontal asymptote is at y equals 1, that horizontal line. All right. And then now further, the y-intercept seem to happen right at 0, -2, 0, -2. And we have a horizontal asymptote at y equals 1. Let's now really record that down on our board. So this line right here, this horizontal asymptote is y equals 1. Okay, and then the y-intercept is happening at 0, -2. Okay. We're going to again try to explain how we arrive at this. And then y equals how we arrive at that horizontal asymptote. But here's the thing, to not waste your time, I'm not going to repeat the transformation table, because here's the thing, we already used the transformation table for the earlier demo functions, the earlier functions from our example 4 part A right there. So I am not going to go through these steps again, but the whole intention of bringing up this example 4 part B on the other board is to confirm these results that we have recognized. So now I'm going to just investigate the graphical property of our -3 times 1/2 of the x and 1/2 to the x plus 1. We're going to investigate the asymptote, the horizontal asymptote, and then the horizontal asymptote and the y-intercept to see if it's agreeing with what we have recognized through the earlier demo problems. So again, I'm not going to waste your time by going through the explanation through the table here anymore. Okay, so I'm gonna legally erase this, because we already used that as an explanation and we already had some generalization, but we were only, remember, we were only about just somewhere over 80% sure like that. So now we want to really push that to a 100% confirm. All right, so allow me to still retain this here. All right, so from the earlier demo problem, that was example 4 part A, then we already came to a generalization. It looks like on any function f of x being in the form of a general form of a c times a to the x plus k right here, then the y-intercept will happen at 0 for x and comma c plus k for y. That's the y-intercept. And then the horizontal asymptote is at y equals k, the value we added to that c times ax right here. So now we want to confirm this result through what we observed on the function g of x being negative 3 times 1/2 to the x plus k plus 1. That's what I meant. Okay, this is c. So this here is c. This here is k. All right, so our y-intercept from, and I wrote it down on the other board right there. Our y-intercept was at 0, 2. This is what we observed and recorded down from the graph we saw on decimals. The y-intercept for this function is at 0, -2. Okay, 0, -2. So we already knew that. But then if we follow with this generalization, well, let's find out what happens. Okay, 0, c is a negative 3 plus 1. And maybe I should even write that in red ink. Negative 3 for c plus 1. Okay, and so now c, so this is y-intercept. If we follow with this, now I'm talking about on the same function, if we follow with that generalization we recognized earlier, are we going to end up with 0, -2? Okay. Yes, we are. And yes, we did. This was, and this is our vertical asymptote. I mean, vertical intercept, y-intercept of our function g of x here, negative 3 times 1/2 to the x plus 1. Because negative 3 plus 1, c plus k right here is that value. And then always it's 0. So now this generalization is confirmed. We confirm. So any function in the form of a c times a to the x plus k has a y-intercept generally at 0, c plus k. We don't even, for this function right here, we don't even have to worry about how the graph being flipped. No matter if it's flipped or not flipped, it's permanently that rule right here to quickly determine the y-intercept, c plus k. 0 for x, c plus k for the y value. That's how we arrived at that. All right, and now the horizontal intercept. The horizontal intercept. So the generalization suggested earlier says the horizontal intercept should be generally at y equals k. Y equals k. Y equals k. Our k value here is 1. So isn't that agreeing with our observation? Okay, so HA for this function, according to the generalization that we have found right here, then it should be at y equals k being 1. Okay, I'm writing that in red ink right now because I'm not perfectly sure yet. Okay, I'm putting question mark right here. All right, and our graph result from this board that we recorded down. Yes, that horizontal line being the horizontal asymptote here was at y equals 1 right there, which is y equals k. All right. So yes, we now confirm that result. All right, so 2 demo problems. It took me a little while to explain, but now we have come to that generality right here. We have come to that generality, and yes, I use the transformation that we've done through example 4 as the solids behind the scene explanations for all of these generalizations. But now it's time to write down that final generalization right there. Okay, so allow me a minute to erase this side of my board. All right, and so now here's the generalization I would like to point out right here. Let's put it this way as a generalization, an exponential function, okay, of the form, okay, an exponential function of the form f of x equals it's the ordinary a to the x function regardless if it's a base above 1 or a base below 1. Positive base, of course. Okay, multiply with a constant coefficient. Doesn't matter positive or negative. Plus k. Okay. So any exponential function of that form, okay, any exponential function of that form has Okay, any exponential function of that form has the following characteristics. All right, so it has the following characteristics. Number one, we generally recognize that that the Y-intercept, Y-intercept is always at 0 for x and c plus k for y. That's one characteristic for them. Okay, and then number two, the horizontal intercept. All right, so horizontal intercept is at, so horizontal asymptote is at y equals k. All right, so these are the two important characteristics for any of the exponential function in a more general form than the ordinary ones. A to the x times c plus k, a to the x times c plus k. All right, and so that's our further generalization that I first brought up example 4, and then I use example 4 to put into some explanations, and then we arrive at this generalization right here. All right, so all right, so in that way, from our general understanding that we have just finalized, okay, then now let's look at the following even more specific case. So ideally speaking, any function, any exponential function, or I shouldn't say ideally speaking, but now the idea is, as far as the general form of an exponential function, we had a lot more. We have c times a to the mx plus b plus k. Okay, and then I did not mention much about that. All of a sudden, I took you into that primary form where I mostly focused to. The subfamily of this is the form where it's simply just a to the x. No need to have that mx plus b here, just ordinary a to the x. And then multiply with a constant k, constant c, constant coefficient c plus k. We focus on this particular form. We primarily put all of our focus into this form, okay? So that we recognize the two major characteristics about the vertical asymptote, the horizontal asymptote and the y-intercept. Okay, or the vertical intercept. Came out right from this general form right here. Okay, but now among these functions, among these general forms right here, okay, so now we're gonna kind of imply our understanding. We're gonna think about as a consequence. Okay, so consequently from this form right here, just think about these, just about those. How about I'm gonna put like this. So what about these? Now we can, with our understanding, we should be able to make the following conclusion. How about some function in the form of just some c multiplied with a to the x? It's even a little shorter than this general form, and this general form is even shorter than that. And then I still did not get to any of that explanation of why we totally skipped the version where we had some horizontal transformations involved right here. I totally skipped that. For now, I still owe viewers an explanation. But all of a sudden I took you and I clearly made my statement. We only gonna focus on this form. And then from that form right here, there's a subfamily, just c times a to the x. And really, so in the way how I see that now, in the way how I see it, this now as a subfamily or as a member in this larger family, it's at constant 0. And so now needless to say, with something like this, just simply a c times a to the x, and then without a constant added, without a constant visually seen, it means we add 0. So now with something like this, then it makes perfect sense that the graph will have horizontal asymptote at horizontal asymptote is at y equals 0. This particular one, and then and I'm only drawing one representative version of that. Okay, 0 comma c right here. Technically, it's 0 comma c plus k, 0 comma c plus k. So again, 0 comma c plus k for the y-intercept for this general version. But hey, our c here is 0. I pointed that out earlier. Okay, and then the y-intercept, the horizontal intercept for this general version, the horizontal intercept HA is happening at y equals k, but k equals 0, and that's why, generally speaking, any of the members in this family where there's a coefficient, some coefficient other than 1, okay, multiplied with an ordinary exponential function, okay, then the graph is simply it could be of rising, going one way from the left to the right, rising. It could be of going one way from the left to the right, falling. And it could also be flipped down the x-axis as well. Okay, but now generally we will always recognize the intercept is at 0 comma c for this short form because k is 0. Okay, and then horizontal asymptotes, okay, is y equals 0 because k value equal to 0 for this specific form right here. All right, and then again, I still keep in mind at this point, I still owe anyone viewing the lesson here an explanation why I totally skipped considering those transformations where we had horizontal transformations applied right there. Okay, and we will get to that, or in another way of saying I totally skipped. I haven't given that explanation of why we only need to focus on this form right here, where only the vertical transformations are involved. Right there. Okay, I haven't delivered that explanation yet. And then sometimes at the end of at the later part of the lecture here, I will get to that point. All right, but so now at this point, with this understanding that we just picked up on a short one like this, okay, on a short one like that, let's push that because surprisingly, this form has a huge amount of applications compared to this general form. So this general form has all of the generalizations of the two major characteristics, but then this form is what you see a lot, most often throughout all of the applications where exponential functions need to come in right there. Okay, and so in that way, for that reason, let's focus on this form right there. All right. So now, even though I wrote a generalization for c times a to the x plus k, but now there will be some point that I will mostly even focus on just this narrow family right there because it has a huge amount of applications that are out there. Okay, just a constant coefficient multiplied with an ordinary exponential. Okay, I mean sometimes extended as an extension, as an extended version. It could be extended as a c multiplied with an a to the mx, but that's about the most. Okay, sometimes it's extended to the form of an f of x equals a c to the mx. But then I will also make that connection why we shouldn't have to be too worried about that. We will know how to handle that. So mostly let's just build our understanding on this form right here. Constant coefficient multiplied with an ordinary a to the x. Okay. All right, so now we are ready for example 5. All right, let's look at example 5 as following. All right, so example 5 is very similar to example 3 we have done earlier. We want to match each of the functions. Match each of the functions here with its graph. All right. So what I'm about to do now, I am going to give you a list of maybe 4 or 5 or even 6 exponential functions. Okay, and now you already had some I believe solid enough understanding regarding the graphs of any of these exponential functions. So now I'm just going to give you a list about 5 or 6 exponential functions written down as an equation, and then from there, after that, I'm going to put on the screen here the graph of those 5 or 6 different ones. They are different color coded, but now we need to match them. And this is why I was saying earlier, it's just like example 3 that we were doing. Okay, so we completely rely on our understanding about the graphs, the graphical properties, and mostly about vertical, the vertical intercepts, Y-intercepts, and the horizontal asymptotes. Okay, we use that to determine, and the shape of the graph, of course. All right, so here we have a list. So how about A is the function, how about y equals 1.5 times 2 to the x. Okay, that's one of them. Okay, and then we have part B, for B, function B on our list right here. So really this is one example. 1.5 to the x. Okay, and then see here I have about 2 times 0.75 to the x. Okay, and then for D I have about y equals 2.75 to the x. And then the last one on my list here I have for E, y equals about 0.25 to the x. Okay, 0.25 to the x. So that's all the list is. 5 functions. Some of those comes with a coefficient, and some of those do not. And when I say comes with a coefficient and do not, really comes with a coefficient other than 1. Okay, and these that I said do not come with a coefficient, really I meant the coefficient in front of that is 1. Okay, so these are just the ordinary exponential function with some base above 1 or some base less than 1. Okay, and these are some exponential function in the form of a c times the a to the x that we have seen, that I introduced right before getting into this example. All right, and so now let's put on the graphs here. I'm going to now show the graphs. All right, so these are the graphs in 5 different colors. I see a red color. Okay, I see a blue, I see a green, I see a purple, and I see a black color. Okay, and so how about for black here, since my marker is already in black color, so how about let me change this to a different color. Okay, to an orange color, for example. Okay, so we got 5 different colors here. Again, red, blue, green, purple, and orange. All right, and so now let's identify which one, say for example, the graph in blue right here, which one among our list is the graph in blue? Which one among our list on the board is the graph in red? Which one among our list is the graph in green right here? We're going to find that out. All right. And so now allow me to put it in a even further zoomed in version right here of that before I put that at the corner of our screen. All right. And so now we have had it all, and the graph is showing on the screen right here at that corner. And I hope it's visible enough. But so these are the ordinary shapes. So now with these, in our experience up to this point, I'm expecting that these must have the y-intercept right at x. Right at y equals 1. 0 for x, 1 for y. So 0, 1, 0, 1, and 0, 1 for the y-intercepts on these 3 guys right here. Okay. So let's look throughout our graph right here. Which one have 0, 1? Which one of, let's look throughout our 5 color graphs right there. Which one goes through 0, 1? There has to be 3 of them. Okay, and those are going to be for these. And then we're going to mix them up and match them up even better. Okay, and then among the graphs there, we're going to look for those that, this one here is quite unique on its own. Doesn't matter what that base is, but it has to have a y-intercept at 0, 1.5 from our understanding, because this is in the form of c times an ordinary exponential function, and then here it's c times an ordinary exponential function, but it's a different constant coefficient already. Okay, so these are easy to recognize, so we can use some of those experience like that. So these 3 will have will share the same common y-intercept, and these 2 will be quite unique on their own like that. All right, and so now let's read the graphs. All right, so now with this one in blue, with this one right here, I recognize immediately there are the 3 graphs going through that common point 0, 1. The blue, the purple, and the orange. These are all going through that point. And so now what caught my attention is the orange is the one that's having the orange graph is the one that's falling down from the left to the right and going through this point. Okay, we have another one falling down from the left to the right, but it's at a different intercept. It has a different intercept. We're gonna get there, but for now the orange one. Okay, and with the shape going falling from the left to the right, it has to be something with a base less than 1, something with a base less than 1, and then it's among the 3. And this is just one way of seeing it. Viewers and learners can also have your own different ways of reasoning it. Okay, but this must be among the 3 graphs where it's just an ordinary exponential function, constant coefficient 1 in front. Okay, so now on my board, these are the 3 functions where the graphs go through one common y-intercept, 0, 1. And these are all base above 1. This is the only one that has that graph falling from the left to the right. And so this has to be the one in the orange color that I was pointing out earlier. Okay? And again, whichever one that we start out, you don't have to start out with the orange one first. Okay? It's just that's my own thought process. And the same problem, if I'm doing it tomorrow, I may approach it differently. Okay? So the point now is that we apply our understanding about the y-intercept and the horizontal asymptote characteristics of an exponential function into our work. So now this one here has to be the orange one. So I'm going to write it down in orange ink right here. Orange, okay? And through the camera, it may be hard to read the orange color right here, but that's about the best I can do right now. Okay, so that has to be the orange one. 0.25 to the x. The graph is the falling down graph, and it goes through that y-intercept at 0, 1, because those are all the only ones we have. Okay. And now I saw these 2 also going through that same point, but among these 2, and like I said, this is just my order of work right at this moment when I'm recording this lecture. Tomorrow, if I'm looking at the same problem, I may approach it differently. Okay, it's just different orders of thought. Any way is going to arrive you at the same destination for this kind of problem, as long as you stay focused on the properties, the understandings, and the characteristics of the graph. Okay, and those 2 characteristics about the y-intercept and the horizontal axis, the horizontal asymptote. So these 2, they're both going up, okay, going through the y-intercept being 0, 1, these 2, but this one has a much higher base right here. They're both above 1. The base is above 1. That's why I was saying it's rising up, but this one here has to be a lot more rapidly. The rising part has to be a lot more rapidly. All right, so let's look at that right now. So on our graph right here, okay, on our graph, the purple and the blue are the only 2 remaining ones after we already ruled out that orange one. So now the purple is a lot more rapidly, okay, compared to the blue one right here. All right, so now we have a clear choice. We have clearly identify which equation is this one and which equation is the blue one as well. Okay. So now on my board, the blue is the one with with the lower base value. So this is the blue one. Okay, it's going up, going through that y-intercept being 0, 1, but it's lower. It's not as rapidly rising as this 2.75 to the x. So this one here now has to be the purple one. All right, so I'm writing that in purple ink right here. All right, purple. Okay, and so now that takes care of three color graphs for us already. The only remaining two here, and these are quite unique. I mentioned that earlier already. I could have started out with those two as first in line as well. That was so, like I said, with this problem, as long as you know what you're doing, the order of how you recognize these shouldn't matter. Okay, this must have a y-intercept at 0, 1.5, regardless of what base that is. Okay, and we only have one unique graph among these here that has that y-intercept at 0, 1.5. And then, or maybe if it's hard to read from the grid, let's focus right here. It has this one here has a y-intercept at 0, 2, and the grid is making it clear that the graph of this guy here goes right through that. And also, let's look at the base here. The base is being less than 1, so it's indicating it's falling from the left to the right. So right here with this one, okay, I'm seeing, and the graph, you can still see the graph right here, but I can now bring it into full screen view right here. So this graph in green is the only graph falling down from the left to the right and has that y-intercept right at 0, 2. All right, perfect. So that now confirms our observation that this one here must be the green version, the green graph. All right, and then that's now for the green graph. The remaining one must be the red one. Okay, so the red one is here, and that's the red graph. And that's how we complete the matching up graphs. We match each of the functions here with its graphs being color coded. All right, so that's how this example 5 works, and it based on our, we only need to rely on our understanding about the horizontal asymptotes and y-intercept. And here mostly it's just y-intercept and the y-intercept and the shape right there, the horizontal asymptotes of these, and you can still see on the picture right now all of these 5 of these graphs are here. They're all having a horizontal asymptote being y equals 0, the x-axis. Okay, because there are k values, see, k plus 0, plus 0, plus 0, plus 0, and plus 0. All right, and that's how it works right there. Okay. All right, so just now I talked about a general form, an exponential function. In this general form, some constant coefficient, and then multiply with an ordinary exponential function, and then plus k. It has any one of these exponential functions has two major characteristics: the y-intercept and the horizontal asymptote. And then in the example 5 earlier that I worked on the other board space right there, I focus on those kind of functions where we can easily recognize. I mean, just focus right on the y-intercept was enough to do a lot of recognizing the graph of an exponential function. So that was the whole example 5 was all about. We based on that one of that major characteristics, the y-intercept of those given the exponential function, to identify which function that is. Okay, and so now horizontal intercepts. Another way of saying horizontal intercepts refer to, and I have explained this earlier as well in our the part of the lecture here, of this video lecture here. But horizontal intercepts, in another way of saying it, refers to and behavior. Okay, and behavior. The left behavior, the left and behavior, and the right and behavior of a graph right there, of a graph. Okay, and so now out of the two characteristics, we're mostly going to focus on the horizontal asymptote nature of an exponential function. So let's look at a c times a to the x plus k right here. Okay, c times a to the x plus k. And so generally speaking, and there are quite a few different cases already depending on the values for c and k right there. So allow me just to focus on two primary cases where the base is greater than 1. So let's assume we have a k value being positive, and then the c value is also being positive, and our graph is going to look like this. Okay, so this value here, this intercept right here is at 0, c plus k. Okay, and then the horizontal asymptote here, and then in the case where our graph is rising, right? And so something like that, then this is a is being greater than 1. Our graph is rising from the left to the right. So we have already understood that this line y equals k is the horizontal asymptote. And so long run behavior, that some textbook calling it, or to me I call that mostly the and behavior according to many other textbooks like that. Then in this way, how I see this particular graph, then see, we talked about if we let x, for this particular graph right here, if we let x go to positive infinity, okay, the right end, because the way how the graph is depending on the positive, depending on the a value, okay, depending on the value of a being either greater than 1 or less than 1, then it will change the long end, the end behavior will run one end going to asymptotes, and the asymptote, and the other end grows to infinity, okay? Or it also grows to negative infinity depending on the c value. In case we have a negative c, then it flips upside down right there, okay? And so in that way, for this particular graph right here, we're looking at, so now a is greater than 1, c is positive. Okay, c is a positive value, just like that case like that. And then what else? I see a k here is generally positive as well. Okay, and whatever that value is, then we're gonna see that the functions, okay, is getting to positive infinity on one end. Okay, and then on the left end, as we're tending out, as we're letting x getting further and further to the left, on the extreme left of the graph right here, that means x is approaching negative infinity. Then the function value, see, vertically it gets close to the line right here. So generally speaking, the line is y equals k, so it goes to k right here. Okay. And I'm only using one case to describe the generality like that. But it's not always like this. It's all about we look at the graph. It's all about we look at the graph. So we got to know the graph, okay? And the graph, that's why we've done those earlier examples, and I've talked in details in the earlier part before we get to this material, so that you can quickly expect what's going to happen to the graph, okay? What will happen to the graph, and then from there we should be able to understand the long run behavior or the end behavior of the graph. So this is not the only case that happened. Don't take this as a generality, okay? Don't get me wrong on that. Don't misunderstand my point. Here I'm just saying the point is we learned from our previous understanding just now, we picked it up, that the graphical property, the horizontal asymptote, where to locate the horizontal asymptote and where to locate the constant value right here. And then from there we should be able to find out together with the information regarding the base of our exponential function. And from there we should be able to expect in mind the shape of our graph. And from there we should be able to expect the end behavior. Okay, so this is not the only situation that can happen. Okay, so don't get me wrong that this is everything. This is always the end behavior of an exponential function like this. Nope, that's not the case. It's only happening when our graph here is having base positive. Above 1, positive c, and then the k is greater than 0 for this case. Because see, I drew the picture where the horizontal line above the x-axis. So now along that way, we got to know the graph, and we got to apply our understanding about the graph, specifically focusing on the two major characteristics that I spent a lot of time on. Let's now put that into the next example, where I call it example 6 right there. Okay, And then here I'm gonna run a computerized version to generate quickly each different problems like that. And so I'm gonna have to constantly switch between the computer screen to show the problem, and then switch back to the board to show our thought process like that. So that we can decide. All right. And so now. All right, so once I've had my the board space here empty and ready for that, then let's look at that the problem. So let's now call that example 6. But I'm also going to let the computer software I'm running here to generate the worded instruction. Then that's only one worded instruction. Okay, so all right, so here we go. This problem wants us, so this is the general worded instruction of the problem here. We want to describe the end, or some textbook is calling it the long run. So describe the end behavior or the long run behavior of our function. How about f of t equals 4 times 3 to the t plus 1. Okay, 4 times the 3 to the t plus 1. So now on my board, the general description that will stay the same for the other problems later on. It's all going to be as a worded problem. Describe the end, okay, or some textbooks are calling it the long run, okay, behavior. All right, so describe the end or long run behavior of. And so now part A, right here, part A, that first function. So I saw that on the screen earlier. How about f of t? Okay, that function was f of t equals, and it was 4 times 3 to the t plus 1. So our function here is in the form of a constant coefficient multiplied with that ordinary exponential function, 3 to the t. Plus the constant k right there. All right, so one more time, I'm writing this down. This is c value, and this is our constant term k right here. Okay, and so now this is how we apply. So before I rush into the answering the question, it's meant to be a fast one, but I still need to document our thought process so that you will catch the solid number of steps right here. So in this form right here, yes, it's in that form of a c times a to the x plus k. All right, so let's find out what to expect. Let's just write down what to expect about the graph right here. As far as the graph, we have a positive k. So the horizontal asymptote has to be here, 1. Okay, and the point is we should be able to do this without using decimals, without using your calculator, your standard graphing calculators, any of your standard graphing calculators. Because now we can quickly do the sketch. Nobody cares about how precise or how accurately you're on scale right there. Nobody cares about that. We got a horizontal asymptote at 1. Okay, the graph could go like this or the graph could go like that. So let's find out. It's a base, a positive base of course, but greater than 1. So it has to be a rising from the left to the right, and together with this constant coefficient being 4. So think about it. The y-intercept had to be at 0, 4 plus 1. The y-intercept is 0, c plus k. So it has to be up here somewhere. 4 plus 1 is a 5. I'm upscale already, but it's okay. But now with that intercept in our horizontal, the asymptote is here. The shape must be, and together with the base being above 1, the shape must be like that. It's a rising shape from the left to the right. How rapid that is, that's not important. Nobody's going to care much about that when we're giving a hand sketch. But that's what but precisely speaking, it has to go through 0, 5 for our y-intercept. Okay, and then it has a horizontal asymptote at y equals 1. This value. Now with this picture right here, we are definitely clear with the answer. Now I can see that as x, and then in the later problems, if we have more problems here, then I don't even have to write this down. Once you see the graph, then your thoughts will lead you properly. Now, as I keep navigating out to the right-hand side, positive infinity, okay, right-hand behavior, then what seems to be the behavior or the vertical behavior of our graph? Our graph vertically, or our function, and I already mistake with the variable's name right here. It should be t, okay? Should be t. So as t goes to positive infinity, our function vertically, in this case, to the right end, our function is vertically rising, okay? Dotted line right here indicating it's vertically rising. All right. That's how it happens, okay? And so now that means I'm indicating positive infinity. And then, so now on the left, as t is tending out to the left end right here, it's approaching to the left end, as we are tracing to the left end of our graph, okay, that means that t is approaching negative infinity. Seems like the graph vertically drops value down to, but down right to that line of y equals 1. It's not even going to cross through it to hit down below down to the t-axis. It's not going to even do that. It's just going to keep getting closer and closer to that line y equals 1. And so now I'm firm that it's going to go to 1. So f of t approaches or getting close to 1. Okay, and so now in that way, we are ready to give that answer with the software I'm running here. And I don't even have to hit submit button here. This is just because I'm running the instructor version, and so it should have that. It should have revealed the answer key here. So right hand behavior. Okay. So let's see if this software program agrees with our conclusion. Yes, it goes to infinity, positive infinity. Left hand behavior right here. The function goes to, and we should select. We should select as our answer choice right here. See. It goes to 1, just like that. All right, and the answer choice is 1. Right here, if we have to answer it, okay, we go to positive infinity, just like that. All right. So now I'm going to run another problem. So now we have a function 4 times 3 to the n minus 4. 4 times 3 to the n minus 4. Okay. And then let's find, so the function here with this software I'm running, then the function generate the variable here is the n variable, okay? And then this is the function right here. So f of n equals 4 times 3 to the n minus 4. All right, so now in part B, our function f of n equals 4 times 3 to the n minus 4. This is again in that form an ordinary, a constant coefficient multiplied with an ordinary exponential function, and then plus with a constant k. This minus 4 is thought of as a plus minus 4 right there. Okay, that's how I'm seeing it. All right. So now once again, let's recognize the Y-intercept property, okay, where we can locate the Y-intercept and where we locate the horizontal asymptote of this, and that's together with the value of the base right here. That should be enough to quickly predict the shape of the graph, and from the shape of the graph, we should be able to answer about the n behavior, the two n behaviors of our function here currently. All right, so now, so I know from this function, okay, Y-intercept now has to be, so drawing some good experience from the earlier work right here. So now Y-intercept for this function has to be at 0, comma c plus k, 0, comma c plus k. C is here, k is here. So that means we have a Y-intercept at 0, comma 0, because that means I shouldn't rush your understanding. So 0, comma 4 plus negative 4, okay, c plus k. That's why I wrote down a little rush earlier, 0, comma 0. That's the Y-intercept. All right, what about horizontal asymptote. Horizontal asymptote is just simply the value k. Okay, value k is -4. So we're looking at y equals -4. We have just enough information now to quickly expect our graph. Here's the graphing space. I don't think I need to draw the space above the x-axis, too spacious. This is the n-axis. This is the y-axis. All right. Our horizontal asymptote is at -4. Okay, it's at -4, right here somewhere, and then we have a y-intercept at this. And this is horizontal asymptote y is -4. Okay, and so if the y-intercept is up here, if the y-intercept is up here, and then the line, the horizontal asymptote is below here, then our graph has to go like this, and it's consistent with the fact that our base is a base greater than 1. The graph has to be a rising graph from the left to the right. Okay, a rising graph from the left to the right. Okay, and so now it has to go as following. All right, it has to go as following, just like that shape again. All right, so now in this, see, this is the y-intercept right there. So now we have enough information to answer at that on the computer software right there. And this is our part B of the example. All right, so now in this function, left n is going to give me, I'm going to select -4, because we know it's asymptotic. Okay, and then yes, the answer should be agreeing with that. All right, the right n goes to, according to how I saw that on the graph earlier, positive infinity. Okay, and then the answer agrees with that as well. Okay, the answer that the machine came out agrees with that. All right. All right, and so now this is our part C of the example. Part C of the example. Okay, just another function for us to look at. We have another function with the variable that's named n. All right, so this is our function, -4 times 1/5 to the n plus 1. So now on my board, I'm going to take a minute writing this down. All right, so part C, our function is about f of n equals -4 times 1/5 to the n plus 1. All right, and once again, clearly we're in that form right there, a coefficient time multiplied with an ordinary the exponential function plus a constant k. All right, so just for you to know, this is our c right here being, this is our c, this is our constant k plus 1 right there. All right, so immediately now we can draw out the following information regarding the two major characteristics right here. Y-intercept, okay, is at 0, c plus k. C plus k. C is -4, k is 1. And so now that means we're looking at 0, -4 plus 1. That's eventually come down at least to 0, -3. We have a y-intercept at 0, -3. All right. And then the horizontal asymptotes must happen at the k value. Okay, the k value is 1. So here I'm looking at y equals 1. Y equals 1. All right, y equals 1. So now, here's how it happens. All right, so here's the graphing space right here. This is what we expect in the graph right here. The horizontal asymptote is here, y equals 1. So I'm picking a point right there. All right, so I call that 1. So y equals 1 is this line right there. All right, and then the vertical, the y-intercept is at 0, -3. So if that's 1, then -3 is kind of like down here. And of course, even if we upscale, that's completely okay. Okay, even if we upscale, that's completely okay. All right, so now the nature is that this function, the base here is less than 1. Okay, the base is less than 1. So if it was the ordinary version, then with the base being less than 1, it has to be going down like this. But now would multiply with a negative, so it's have to flip over. So it has to be the mirror image. So without a negative coefficient, base less than 1 means it's a falling down shape. But now with a negative coefficient multiplied in front, it's not this shape, but it's not this falling shape, but it's this shape here being the reflection through the x-axis, or just the flip over version. So now that means right here, and since the y-intercept is right down there already, 0, negative 3, okay, and so I'm going to draw the version as following. That's what it looks like. Okay, that's what it looks like. All right, that's what it looks like. Okay, so multiplying a negative is going to make it flipped compared to the actual version, parent's version, and then it's going to be crossing at that intercept and y-intercept, and then that's asymptotic to that horizontal line right there. All right, so now looking at this graph, we have a clear understanding about the end behavior of that graph right there. All right, so now on my computer software right there. Okay, so left end, I'm expecting it dropping down to negative infinity as we saw on the shape earlier. Okay, so I selected that. Okay, the right end, and then that agrees with my answer. The right end here goes to, it should go to 1, because it's, so one of the end has to be asymptotic. One of the end has to be asymptotic. Okay, and so we already know one end goes to negative infinity, the other end has to go to the asymptote. And so now that agrees with our the value right there. All right, so that's how we have done part C of the example. All right, so now we arrive at our part D of the example. Another quick one for us to try right here. How about minus 5 times, so it's f of x this time, minus 5 times 2 to the x minus 1. Okay, minus 5 times 2 to the x minus 1. Okay, so now let me spend some time writing this down. And then I'm going to retain this information I've had. All right, so this is now part D of our example. The function is f of x, and that equals negative 5 times 2 to the x, and I'm subtracting 1. Okay, negative 5 times 2 to the x and minus 1. And so this function, again, this is our C, and it's in that form, that general form right there. And then this is, with that right here, it means we're adding with a negative 1. Okay, so our k is here, negative 1. That's the k, and that's the k. All right, so now from this, we already have a good sense about the y-intercept and the horizontal asymptote right here. Horizontal asymptote is easily at negative 1. Y equals negative 1. That's line below the x-axis. Y equals negative 1. Y-intercept here is going to be 0, c plus k. 0, c plus k. C is negative 5. Okay, and then plus k with plus another negative 1, which is negative 5 minus 1 right there. So we're looking at 0, negative 6. Okay, 0, negative 6. 0, negative 6. All right, so let's put in our graph right here. So with the graphing space, all right, so negative 1, the horizontal asymptote is somewhere down here. Okay, that's y equals negative 1. Okay, and then the y-intercept is even way down. Okay, the y-intercept is even way down, 0, negative 6. Forgive me if I'm off scale right there. All right. So now it's time to put in the actual shape. Now, the beginning shape could have been, that's why I'm leaving that in dots right there. Okay, the original parent function is positive, base greater than 1, so it should be rising from the left to the right, but now with a negative, with a negative coefficient here, it's going to flip the shape to the thing like this, the shape exactly like this, rising from the left to the right, but now it's going to flip over the x-axis. and then it has to be, make sure it has to be below this y-intercept as well. I mean this horizontal, the asymptote as well. And so now in that way, here's what it looks like. So it must go that way. All right, it must go that way. Okay, so asymptotic on the left end, and then it's dropping negative infinity on the right end of the graph like that. All right. And so now we are ready to provide an answer to that. Okay, so now left end goes to the asymptotic side right there. So the asymptotic, it's asymptotic at -1. So I'm going to select -1, and the answer agrees with that. Okay, the right end drops down to negative infinity. Okay, and the answer agrees with that. All right, and so that's how we did example 6 earlier. Okay, so now at this point, before I'm concluding out this final, before I'm concluding out on this particular topic about all the graphical understandings, primarily we focus on the horizontal asymptote and the intercept, the y-intercept, and then I'm primarily focused on this form, even though we had the horizontal transformations applied right there. So if I have some time, because I don't feel it's that important anymore, but if I have some time, I will make a separate recording on on how we apply the horizontal asymptotes on our to take care of the other forms of the c times a to the mx plus b plus k right there. But that's not important. That's why, like I said, right here, in this lecture right here, I'm not going to include that part. Okay, so if I have some time, I'm going to post another video, separate video lecture for that. Okay, and then if you want to learn, you can feel free to find that other video lecture right there. Okay, but now why is that? I mean, why did I not focus on those horizontal transformations? Why did I not focus on any of those horizontal transformations? Because again, recall at the end of our introduction lecture on the exponential function. Wait a minute. Again, we thought that exponential functions include more members, like more generally, even more generally, c times a to the mx plus k. I mean, c times a to the mx plus b, some linear expression here, and then with a plus a constant. But why is it all of a sudden? I made that statement earlier that we only need to focus on this form. And then even among the general form, we just need to primarily focus on those c times a to the x only as our primary shot there, primary goal right there. Why is that? Okay, so now at this point, whoever learning in this video lessons, you are at the pre-calculus level. Your algebra understanding is mature enough at this point. At some point, I have to bring in some mathematical proof. I mean, it's not even a formal one yet, but at least it brings in some of your past understanding. And I expect you review some of your algebra before we see this. But it should be the basic stuff, okay? And it brings it clear, it brings out to light why we only need to focus on this general form where only the vertical transformations involved, so that we can quickly identify the y-intercept and the horizontal intercept, and that should be it ever. We don't really need to worry about the horizontal transformations as much. Okay, here's why. All right, so now I'm gonna erase my board here. All right, so this is my explanation of why we only need to focus on the, see, our goal now is to find out why we, allow me to write, to put that in. Of course, it's not proper with the proper grammar, but why only considers c times a to the x plus k. Why is it only so? Okay, so let's find out. Let's be as crazy as we can. So this time I'm going to really let my own creativity to kick in and come up with crazy expression as much as possible. Okay? So we already agree that generally any function of x in the form as following: c times a to the mx plus b plus the constant k. Anything like this? is officially an exponential function. Okay, and so now let's come up with one quick example. How about my mind right now is telling me let's go with point 35. So point 35 is the base. I'm going to raise this to the x, okay? And then how about my mind right now tells me a negative number, minus 3. Okay, so I'm going to change that to negative 3. My mind right now, so right now we're in that form of ax plus negative 3. And my mind just now tells me how about a constant positive 4. Okay, so now it's c times the ordinary functions. C times a to the x plus negative 3. And everything I'm moving right now is completely live with my own creativity. It randomly comes out. And now how about my mind just randomly generated for me a minus 3 here. And then a plus 5 there. Let's, as I said earlier, let things be as crazy as it can. But see, this is our deadliest, I have to say, deadliest exponential function form right there. And yes, it's in that most general form of all that covers all exponential functions out there. Okay, so it got a linear, the expression in the exponential part right here. And there's a base or whatever here, greater than 1 or less than 1, we see it, whatever is here as is. Okay, so why is it that we only focus to something like this, whereas be aware that functions like this exist out there. So here's how I can make my way, here's how I can use the algebra to purposely make something like this to appear, only in this form. Like I said, from the beginning, it looks completely in this form where we have a linear like a minus 3x plus 5 here, not a simple x. And then there's c and there's k here. But now I'm going to tell you, I'm going to make way for this to appear only in that form. C multiplied with an ordinary a to the x plus k. Okay, seems like a huge challenge, but let me tell you, your algebra experience is enough for you to follow through with this step of mine right here. And it's not a formal mathematical proof, but it's close enough. I'm proving through examples, okay? And for people who have some serious intentions in math and do plan to follow on with, to the higher course right there, I suggest taking this quick little work I'm doing right here. Let's leave the 4 coefficient there by itself. Okay, according to the rule of exponents, you see this work right here is the minus 3x plus 5, so we can separate it out as a 0.35 raised to the negative 3x times 0.35 to the 5th power, and then minus 3. I moved from this step to that step. I only broke that down to that part right there, but it completely aligns with the rules of algebra, the rules of exponents. See, think of this, think of the two terms here, the minus 3x plus 5 is an addition of 2 separate powers. And so we can turn that, recall from your property that a to the m plus n, a to a power being a sum of some 2 other numbers, we can write it as a to the m times a to the n. That's what I just did. All right, and so in that case, now I realize, oh, wait a minute, this 0.35 to the 5th power is simply just another constant value, just another constant coefficient. So I'm going to multiply that together with this. I'm going to bring it in front and multiply that together with this 4 right here. All right, and so now in my next step, my function becomes the following. Okay, so really, and I'm not really going to rush over to my desk and grab a calculator or anything like that. Nope, I'm not going to worry about that. So now I'm going to have 4 times whatever 0.35 to the 5th power. Okay, that's one part. I keep it there, and I know it will have a definite value. I didn't bother hopping over to my desk, grabbing out a calculator to grab out a calculator. But now it's a coefficient multiplied with 0.35 raised to the power negative 3x. So all of a sudden, the exponential function already reduced significantly. We didn't have that plus 5 anymore. All right, and then minus 3. So the minus 3 is still that constant k right there. All right, one more step, ladies and gentlemen. Okay, so just look at this 0.35 all raised to the power 3 minus 3x right here. Minus 3x, in our understanding, in our algebraic understanding at this point, minus 3x means minus 3 times x. Minus 3 times x. Minus 3 times x. Okay, another property. At this point, I think I need the space on the other board, so I've left this here long enough. Allow me to erase that. Okay. All right, so currently I'm at 4 times 0.35 to the 5th power. Okay, and I see all this here as some value, some definite value. As I said earlier, some definite value. I just didn't bother grabbing a calculator to pull out an actual value for this. I bet it's going to go pretty nasty in decimal. That's why I leave it right now like that for now. And then I was explaining earlier before I jump to this board that this minus 3x means minus 3 times x, and then minus another 3. And every number here in this problem came out completely from my own creativity. And I tried to be as crazy as I could. Okay? And so now the minus 3 here, now we've had another rule along the algebraic understanding that you've already had. A base a raised to a power m times n. You can think of this as a to the m times raised to another power n. That's one way of seeing it. Or you can think of that as a to the n times m. Basically, anytime you have a power raised to another power, a power raised to another power, a power raised to another power, then we come up to an overall power being the product of these two levels of powers. Okay, and so here, that means here specifically applying to our case here, this is what I'm doing. This is why, if you're taking a class with me for calculus, no matter how far you go to calculus, calculus 3, calculus 4, depending on where in the nation you're taking the class with, you will hear me constantly yelling at the students, in a kind way. You got to get your algebra going. You got to get your algebra going. Okay? Never look down to these skills right there. Maybe in your past, you didn't emphasize too much, but now it's time to really emphasize on these things you have already picked up. Okay? 0.35 raised to the power negative 3 times x. Now I can see this as a 0.35 to the negative 3 power, and we raise that to the x power. Okay, 0.35 to the negative 3 raised to the x power. Isn't this another known value? Isn't this another known value? Okay, and so now here's how I'm seeing it. 4 times 0.35 to the 5th times all of that here is now written as 0.35 raised to the negative 3 power. Okay, and to the x minus 3. The expression looks a little wild, I admit. But ladies and gentlemen, let me announce this to you. I keep saying a known value because if I use a calculator to come out with a value, this is my a over here. So now I'm in a to the x. All right. If I use a calculator and calculate that value, I come out with some value, I call that c. So it's c times a to the x. And then this is my permanent value plus negative 3. So that's my k right here. And that's how, as I said earlier, no matter how your beginning function looks like, you can always bring it. You can always bring your very general form of an exponential function into this specific general form, c times an ordinary a to the x plus k that I specifically focused on. All right, and because this is making it easy for us to immediately identify the y-intercept and the the horizontal intercept. Okay, so a little more extra notes for anyone, because right now I'm just the two lectures. The one before this was the introduction to all the exponential functions, and here we're studying all the graphical properties of that. I have not mentioned at all. I didn't have a chance at all, because otherwise it's going to be very lengthy, and that will come in a different the video lecture right here. But you have not seen any applications, any of the applications of these exponential functions yet. It's a whole unlimited world out there about the applications of all of these exponential functions. That's why it's so worth your attention to look at these functions. And so now, out of so many different forms that I generally regard it as this general form right here, okay? And I've made it clear at the end of our lecture where I introduced about exponential function. I show one example when I made way to make it clear that any function, regardless of how ugly it is, you can always bring it back. You can always find a way to bring it back to this primary form that I introduced earlier in this particular lecture. Doing that, at the end result, it's going to make the work easier for us. First thing, to recognize the graphs, y-intercept and horizontal asymptote. And then furthermore, I talked about applications. You will be surprised about the amount of applications of those exponential functions out there that involves these forms. And so now later on, for you to prepare you for the later lectures, just still within our course, to prepare you for the later lectures, when we get to the exponential, to the applications of the exponential function, you will commonly see the following. So when it comes to applications, okay? When it comes to applications, we will a lot of times focus on the kind of function where it's a coefficient c multiplied with a value, but then to a power mx. Okay, c times a constant coefficient like that, but instead of multiply with an ordinary like this, just mx. And of course, like this short form right here is a plus k, where k is 0. So now you have just learned that trick right here. A to the mx, and provided m is a coefficient in front of the x, then a to the m itself is a known value. So right now it's maybe running on a little bit. As far as the applications out there, my point is, as far as the applications that you will later on be exposed to, there will be a lot of occasions where you deal with those exponential functions. C times a to the mx plus 0. This form right here primarily exists a lot among your applications. But again, how do I see this? As one family of, in this, that I put in a red box right here. Constant coefficient, needless to say, but then only need to multiply with an a to the x ordinarily. But here it's an a to the mx. Okay, so how do I see that? Because so now c times a to the mx, I see this as c times a to the m to the x. And this is how I'm seeing that. See, this is one base here. A to the m is the base raised to an x. So now we're in that form, c times a coefficient times an ordinary exponential function plus constant k 0. Now we're back to that form where we can easily identify the y-intercept and horizontal asymptote right out from this. So anything like this will easily come out with horizontal asymptote being, okay, the line y equals 0 already, because k is 0. All right, and then this value right, depending on the c right here, sometimes it's a graph going up, sometimes it's a graph going down, sometimes it's a graph going one way like this. Okay, you will have all your times exploring that when we get to the applications. Again, I'm just making it clear that no matter how diverse the general form of an exponential function is, okay, but we can always make that. So any exponential function, any general exponential function can be rewritten, can be re-expressed in this form right here. All right, so my bottom line before I completely close down with this lecture over here. Many textbooks made this statement. So now allow me to erase this. So just now I've done all of that explanation. So now I'm going to make that final statement here before we close down this lecture. Any exponential function, okay, of the form f of x equals c times a to the mx plus b plus k, okay, any function like that can be, how about, to really emphasize, textbooks usually don't come with this term here, but I can say that, okay, can always be rewritten in the form. So it's the same function, it's just a different form. How are we writing it? So any form like this can always be rewritten in a form f of x equals, all right, so a big C multiplied with a capital A, because it's all changed the base. We've all seen that through the work. It's not the same base anymore, but it's still in that form, okay, plus K. All right. And this is the form that we primarily focus to. All right, so that is everything we need to learn as far as, up to this point, introduction to the exponential function. And now we finished with all the graphical properties of that. So I did not say I have covered all examples about the graphical properties yet, but if I have anything in mind, I will record those video lectures as short little application problems. Okay, it's not the application problem to the world application problem, but it's just the application of problem, how we apply these quick understanding into into various different situations right there. And there in those little problems, there are no hard rule of how we apply, and that's why I have to, those have to be revealed after you have seen enough details, all of the comprehensive amount of details here throughout all the graphical properties of an exponential function. Okay.